In this video, we're going to explore the concepts of mass percent and percent composition of a compound. So our first concept we're going to see is something called the law of definite proportions, which basically just states that the elements in a compound, so let's say water, are always found in the same proportions by mass. So regardless of where you get this H2O from, whether it's from the tap or a lake or a river or from some water bottle company A or water bottle company B, water will always have 11% hydrogen, shouldn't say water, 11% hydrogen, and 89% oxygen by mass. Not by atoms, because there's 3 atoms and that would be 66% hydrogen and 33% oxygen, but by mass, the mass of hydrogen and the mass of oxygen. So again, wherever that water's from, according to the law of definite proportions, that water will have the same proportion by mass of its elements, 11% of the hydrogen and 89% of the oxygen. And so to find the mass percent of an element in a compound, you can use this formula over here. Mass percent of element X is equal to mass of X in the compound. So X could be anything. If we're looking at water and we're trying to figure out the mass percent of H, well, X will be H in this case. Over the total mass of the compound, multiply it by 100. Kind of like finding your mark on a test. You do your mark divided by the total of the test times 100, and that gives you the percentage that you obtain on that test. So mass percent of an element specifically is the percentage of mass that element makes up in the compound, that specific element that you want to study. You'll also see another term called the percentage composition. That basically means find the mass percent of all the elements in a compound. So a question could ask, find the mass percent of hydrogen in water. And you just have to find the mass percent for the element hydrogen in water. But a question could also ask, find a percentage composition of water. That means you have to find the mass percent of hydrogen and then the mass percent of oxygen. So again, I just want to emphasize that according to the law of definite proportion, wherever you get your water from, the water will always have the same percentage composition. 11% water, 11% hydrogen, 89% oxygen. Here's another example. We have K2Cr2O7, and over here you can see the percentage composition that was calculated. So to find the percentage composition, you find the mass percent of all the elements in that compound. So here we can see at 38% by mass is oxygen. We can see that 35% by mass is chromium, and then 27% by mass is potassium. And if you add them all together, you would of course get 100% because you only have 3 elements that make up that compound. So these tables here just illustrate the idea of the law of definite proportion. An analysis was done on a compound. We don't really know what the compound was. We just have it here. Let's just say it's a hypothetical one, CXHYOZ. We don't know what these subscripts are, but it doesn't really matter. Here's what matters more. We have 3 samples that we analyze: sample 1, sample 2, sample 3. And you'll notice that the 3 samples have different masses. So sample 1's 2, 2 is 4 grams, and 3 is 6 grams. And we did an analysis. We put it through some machine that you'll learn about later on, and we figured out the mass of carbon, the mass of hydrogen, the mass of oxygen in each of them. And you'll notice this, yes, they have different masses. Obviously the one that has the highest mass is the highest mass of all the elements. But let's go and take a look at our percentage analysis. So regardless of the size of the sample, regardless of where the sample was from and also its size, the percentage by mass is always the same. For each of the samples, it's 40% carbon. For each of the samples, it's 8.40% hydrogen, and for each of the samples is 51.5% oxygen, regardless of where the sample came from. And that's just an example of the law of definite proportions. The scientist who came up with the law of definite proportions was Joseph Proust. He came up with it in 1794. I'm going to briefly talk about a few experiments that were done in order to come up with what the law of definite proportions was. I do want you to keep in mind that just like with any other science, anytime we do give you a law or a concept, it's not something that we make up. It's not something that was just determined in a day. It was many, many years of experiments, many scientists working together using experimental data to come up with these laws, to establish these laws. So don't just think they came up with it very easily. It does take a lot of time. So one type of experiment that used to be done by Proust to figure out the law of definite proportions was basically breaking down compounds. So here we have some copper carbonate, 103 grams of it, and when it was broken down it would become some copper, some oxygen, and some carbon. And scientists found that regardless of the size of this sample, whether it was 103 grams or 206 grams, we always got the same proportions by mass, or the same percentages. So yes, these masses here would have been different. If you had double the sample size, you'd have double the masses here. But when you get the percentage, it's still the same percentage for each element, so still the same percentage composition. So that being said, each compound is always going to have the same percentage composition, regardless of sample size or source of the sample. Another experiment that was used to determine the law of definite proportion was an experiment done by a scientist named Berzelius. So over here, you can see that this is the original recipe to make lead sulfide. Okay, so if you combine 10 grams of lead and 1.56 grams of sulfur, you'll get 11.56 grams of lead sulfide. And that's how they combine perfectly. There's nothing left over, it's just all lead sulfide. So what scientists decided to do is they said, let's try playing with the recipe a bit. Let's keep our 10 grams of lead, but increase the amount of sulfur that we have and see if we'll get lead sulfide with more sulfur inside of it, so a new combination. But it was interesting. You'll notice here that we still got the same mass of lead sulfide and then just leftover sulfur. That extra sulfur we added in there did not combine with the lead to make a different kind of lead sulfide. We still had the same proportions by mass within the lead sulfide, and the excess was just left over. Then we tried another experiment. We said, maybe that was just sulfur. Maybe sulfur doesn't react that way. Let's try instead keeping sulfur the same as the original, but increasing the amount of lead. So here we can see that we have more lead than the original recipe. But same result. We got 11.56 grams of lead sulfide, so same percentage composition, and then that excess lead, that leftover lead, well, was just left over. It didn't react in there. So this was another experiment that supported that law of definite proportions. The lead and the sulfur would always have the same percent by mass within the compound, lead sulfide. You wouldn't have that excess sulfur would not change or increase the percentage of sulfur in the compound. The excess lead would not change or increase the percentage of lead in the compound. So in case you haven't figured this out yet, each compound has their own percentage composition. So for example, if we have H2O and H2O2, different compounds, but made up of the same elements, you'd think, well, why don't they have the same properties? Because they're made up of the same elements. And it makes a big difference. Here we have one oxygen, here we have two oxygens. So the fact that they have different numbers of oxygens gives them different properties. This stuff here you need to drink to live, and this stuff here, if it's too concentrated and you drink it, you're going to get hurt. You use it to bleach your hair, you might use it to clean wounds, but the idea is that they have different proportions by mass. They have different percentage compositions. So for water, it's 11% hydrogen by mass and 89% oxygen by mass. For the hydrogen peroxide, with that extra oxygen in there, when you do your calculations, it comes up to 5.9% hydrogen by mass and then 94.1% oxygen by mass. I know you might not think it's a big difference, but that does make a big difference in terms of the properties of the compounds. So if you have different proportions or different percentage composition, what that means is you'll have different properties for your compounds, even if they're made up of the same type of element, hydrogen, oxygen, but different percentage compositions. So now we're going to take a look at how to figure out the percentage composition of a compound. There's two ways to do it. sometimes you won't know the chemical formula of a compound. So when I say chemical formula, you won't know that you have a compound called H2O. You'll just know you have a compound made up of H and O, and you somehow have to figure out the percentage composition. To do that, you need to have mass data. So you'll have data saying, well, we have a sample of a compound. We figured out there's this many grams of hydrogen in that sample and this many grams of oxygen in that sample. Find the percentage composition. We don't know what the formula of the compound is. We don't know if it's H2O. We don't know if it's H2O2. We just know the masses of the elements. So you can use that mass data without a formula to figure out the percentage composition. And we'll go over and do that in a bit. But you can use an electronic balance to mass things out. And the second method is from a chemical formula. Sometimes you might have the chemical formula but no mass data. So we might know it's exactly H2O, and we could use our knowledge of the molar masses and our knowledge of molar masses to actually find the percentage composition of a compound. So if you don't have the formula, you're going to need mass data. If you don't have mass data but you have a formula, then you're going to use the formula molar mass concept. And we'll do some examples in just a bit. So over here, I just want to draw your attention to an example that you should be able to figure out. And I want you to remember that what we're learning is not too different than things you've already seen before. You know how to actually do this. It's just that we're dealing with it at the microscopic level, the atomic level, a very, very small level, but it applies the same way as it would in any section of the world. So here we have a compound called vanillin. It's C8H8O3. And in this pie chart, we figured out the percentage composition of vanillin. We saw that there's 63.1% carbon, 31.6% oxygen, and 5.3% hydrogen in any sample size of vanillin. It doesn't matter what it is. So the question here is, let's say you had 50 grams of vanillin in a test tube. Knowing this percentage composition, figure out, well, how many grams of O, H, and C there would be. I'm not going to do all of this for you. I'm going to do one sample with you. Let's choose to do the percentage of O, or the mass of O in this test tube with 50 grams of vanillin. So first I would look at my percentage composition. I would know, or my mass percent of oxygen actually. So this whole pie chart is my percentage composition, and each little section is a mass percent of an element. So mass percent of oxygen is 31.6%. That means in any sample size of vanillin, there's 31.6% that's going to make up oxygen. So you're finding basically a number based on that percentage. So if I say a test is out of 25 and you got 50%, you would do your 50% multiplied by 25 to find the raw mark, that mark you got out of 25. Or if I said a test is out of 100, just to make it a bit easier. Test is out of 100 and I said you got 80%. That means you got 80 out of 100. You did 0.8 times 100, because that's 80%, gives you 80. So over here, our test is out of 50 grams. And I want to find the grams of oxygen, the mass of oxygen. So I'm going to do 31.6%. Now, what this actually means, this 31.6%, this actually means, and I'm going to rewrite it here, is 0.316. Right? Because it's percent per 100. So when you're doing this calculation, you need to make sure that that percentage is converted into its decimal form in order to use it properly. If you do 31.6 times 50, you're not calculating percentage anymore. So make sure that you first divide this percentage by 100 to get your decimal value. So that's our 31.6%. You're going to multiply it by the total mass of the compound, 50 grams. You're going to put that in your calculator. So I have my calculator with me. You should have yours too to try these out, see if you get the same answer. 0.316 times 50 gives you 15.8 grams of oxygen. Now we need to follow our significant figure rules. Here we have 3 sig figs. Here we have 2 sig figs. So since it's a multiplication, we need to make sure that we, let me just write sig figs here so you don't think I'm dividing. We need to make sure we use the least number of sig figs, so that's 2. So we need to round this to 16 grams. Some students have the tendency to put 16.0. Don't do that, because what that means is now there's 3 significant figures here. That's what that means. You want to leave it at 2 sig figs as your final answer. If you leave it as 16.0, now you're saying we're certain about the 1, we're certain about the 6, but we're not really certain about the 0. So you know, we might be off there. It might be 16.1, 16.2. We are trying to establish that we are not really certain about that the 6 over here. It could be 17, it could be 15, right? We're not precise enough to know that we're certain about that that 6 there. So don't break that significant figure rule. So these are the type of problems you should be able to do, even without knowing how to calculate percentage composition or mass percent of an element. All right, so now we're going to do an example. We're going to try to figure out the mass percent of an element using, or of an element, or the percentage composition of a compound using mass data. So here we have the mass of a compound given to us, 48.72 grams. And an analysis was done and we found that there's 32.69 grams of zinc and 16.03 grams of sulfur. What's the percentage composition? So that means you need to find the mass percent of each element in the compound. So first I write down my given information. I have 32.69 grams of zinc, and I have 16.03 grams of sulfur. My total mass is given to me, but let me just double check to make sure it's right. 16.03 plus 32.69, and yes, it's 48.72 grams. So that's figured out. It's given to us in the question. If it's not given to you in the question, you have to make sure you add up all the masses of the elements, and then you get your grams. So again, it's really logical. It's nothing too complex. It's almost so simple that that's why some students might find it difficult, but it's fairly logical. So we're asked to find the percentage composition. That means we need to find the mass percent of each element. So we're going to start off by, here's our formula, mass percent of element X. We're going to start off by trying to find the mass percent of zinc. So mass percent of zinc is the mass of zinc in the compound divided by the mass of the compound total times 100%. So this one's done for us here. We have 32.69 grams divided by 48.72, cross grams out. It's multiplied by 100%, and we get 67.1%. Some of you may have realized my significant figures rules were not followed, so I'm going to redo that to get the significant figures done properly. 32.69 divided by 48.72 times 100. So don't count the 100 in your sig figs, but because it's the 100% there. But do count the mass data that you have. So you'll notice that I have 4 sig figs. There should be 4 sig figs left at the end. So I can do, in my calculator, I get 67.0. Let me just see, 67.09. So I want to get 4 sig figs here. So what I can do is I could round up. And when I round up, that'll give me 67.10%. So just make sure you have that sig fig added there, because we had 4 and 4 in the question. Mass percent of sulfur, same idea. We take our mass of sulfur over the mass of the compound total. And we don't know what the compound is. We don't know its formula, so we can't write mass of zinc sulfide. We don't know if that's what it's going to be. So mass of S, mass percent of S is going to be our 16.03 grams over our 48.72 grams. Put your units in. You can cancel grams out, multiply that by 100%. And then don't forget our sig figs are off here, so we're going to have to recalculate that. 16.03 divided by 48.72. Multiply that by 100. And we get 32.90%. I always recommend writing a statement at the end just because it shows me that you know what the question's about, and it might also help you to make sense of what the question's about as well. So the compound consists of 32.90% sulfur, of 67.10% zinc by mass, and so if you added both these up to check your work, you should get pretty close to 100%. I mean, you might get 99.99999, but that's pretty close to 100%. If you get 98, it's a bit far off. You might have rounded too much or made a mistake in your calculation. I would say you really need to be in that 99.999 area and 100%-ish area. Of course, if there's mass, if there's actual labs that you did, you might have lost product, and there might be a greater discrepancy, but in the problem that I typically give you from a book or from a problem set, you'll be pretty close. So here you have some more sample problems to attempt. I know this is the same problem from the example, but I always recommend that students retry the example done in class first as a model, so then you can go and try the other problems. If you don't understand the problem done in class, you're not going to magically all of a sudden understand the other problems that are very similar to it. So always retry, use the notes that your teacher did in class, and you'll understand the concept more effectively. There's a few problems you can do in your textbook. Make sure that you're following the course outline that was posted online for you. You can also do some problems in the problem set 24 to 30. We're not done yet. We're going to do one more sample problem together. We're going to take a look at how you could figure out the percentage composition of a compound from its formula. So you don't have mass data, you don't really need it because you know the formula of the compound. Here we have some more practice problems along with solutions and answers. So now we're going to take a look at a compound called cinnamaldehyde, and it gives cinnamon its delicious, its wonderful odor. And the reason I'm choosing that compound is because one of my favorite treats is always some good old Cinnabon or the cinnamon roll frosted from Tim Hortons. So let's get started. So here we have, again, same idea, mass percent of element X is going to be mass of X in the compound divided by total mass. Now in this case we have a chemical formula. So if you have the chemical formula, you can actually use the molar masses as your masses in the compound. I'm going to walk you through how to do this. So we're going to take cinnamaldehyde as the example, C9H8O. We know the formula. And what you're going to do is you're going to figure out the molar mass of the C9H8O. So if you look in your periodic table, you have the molar mass of carbon is 12.01. Now, that's grams per mole. And we're going to change that in just a bit, but we'll see why. For hydrogen, it's 1.01. Grams per mole. For oxygen, it's 16.00 grams per mole. And what we're going to do is we're going to figure out our molar mass by doing the steps that you learned in class. So you're going to do molar mass of the compound, which is vanillin, or not vanillin, sorry, I have vanilla on the mind from before. Cinnamaldehyde, C9H8O. I'm not going to write it all out, I'm just going to do it in my calculator. But you're going to have your molar mass of carbon times 9, molar mass of hydrogen times 8, molar mass of oxygen. And you're going to add them all up together, and that'll give you the molar mass of the compound. And we get 132.17 grams per mole. You could show your work here and have your final answer. But what I want to emphasize is that you'll notice that the first step is actually assume 1 mole of the compound. So if you assume 1 mole of the compound, think about the mass in grams you would have. Think about what the molar mass means. Molar mass means the mass of 1 mole of a compound. So if I have a mole of cinnamaldehyde, what will my mass in grams be? If I have 1 mole of it. You can use your formula if you want to. You could do your mass times molar, your mole times molar mass, and you'll get 132.17. And that makes sense. It's grams per mole. If you have 1 mole of the compound, that means you have 132.17 grams. So we have 132.17 grams of the compound. Now, you technically could have just stayed with your molar masses and done the rest of the problem with the molar masses. It's the same thing. You could have just done grams per mole, but we just assume 1 mole, and we only have to use the unit gram in there. It's a bit easier to do. So now we're going to go and figure out our mass percent of each element in the compound, because we were asked for the percentage composition. So let's start off with the mass percent of oxygen. So we're going to do our molar mass of oxygen, which is 16.00. Now remember that we assumed 1 mole, so we're just going to put grams, divided by our molar mass of the compound, 132.17. And then we're going to multiply that by 100%. And that's going to give us, so let's try that out, 16 divided by 132.17 times 100. We want to keep 4 significant figures, so that'll give us 12.11%. 12.11%. Notice that sometimes the numbers I typed in did not have the correct number of significant figures, so we'll correct those as we go. 12.11%, and you can move ahead if you want and try these out yourself. Mass percent of hydrogen, so don't make the mistake of just doing 1.01 divided by 132.17. Take a look carefully at the compound. The compound has 8 hydrogens in it, so you need to make sure you're doing your 1.01 times 8 to give you your 8.08 grams. Divide that by the total mass of the compound, 132.17 grams. Multiply that by 100%, and again we're going to want, now in this case we're going to want to keep 3 significant figures. So 8.08 divided by 132.17 times 100, and we get 6.11%. And then we'll do the same thing for our carbon. Remember, you're not just doing the molar mass of 1 carbon, you're doing the molar mass of 9 carbons in this case. So you do your 12.01 times 9, 108.09 grams over 132.17 grams times 100%. And we get 132.17 times 100. We want to keep, in this case, 5 significant figures, so we get 81.781 grams, or 81.781%. So 81.781%. So let's just double check that one. I gotta make sure it's 108.09 divided by 132.17. You can double check your work if you're unsure. 81.781%. Okay, then you can add them up. So you'll notice that when we add our percentages up, we should get close to 100. So let's try this out. So 81.78 plus 12.11 plus 6.11. We get a little over 100 only because of the way we rounded, but roughly 100%. Typically, I recommend that you keep all your decimals in when you're trying to add them all up at the end, just to get as close as possible to the 100 as possible. When you're rounding up and down, you're going to be a little bit off from the 100. You might be lower or higher depending on how much you rounded up or rounded down. But it's close to 100, and here we have our percentage composition: mass percent of O, mass percent of H, mass percent of C. The most common mistake, again, is students not multiplying the proper molar masses by the subscripts in the compound. So make sure you do that, otherwise you will make that careless mistake and get a lower percentage mass percent for the element if you don't multiply it by how many of that element there actually is in that particular compound. So here there are some more practice problems. You have the formulas, and you need to find the percentage composition of the elements in the compound. So read the question carefully. If you're asked for percentage composition or percent composition, you need to find the mass percent of every single element in that compound. Here you can see find the mass percent of hydrogen. So you don't have to find the mass percent of every element, you just need to find the mass percent of hydrogen in that compound in order to fully solve the problem. One very important application of this percentage composition, and mass percent concept is in the field of metal refining. When you have an ore and you want to extract some metal from it to make a profit, you might need to make some decisions as to whether or not it's worth investing your time, money, and energy into that ore to get the metal you're trying to extract. So here you have a great sample problem that you can attempt to determine how much of a certain metal you can get from an ore. So here we have manganese oxide. It's a compound with some manganese and oxygen in it. What you need to do is first find the percent composition of manganese, the manganese ore, so the percent composition, not just the mass percent of manganese. And then you need to use your answer from A to find, well, how much manganese can you actually get if this ore was 250 kilograms? So how many kilograms of manganese could you get from it? There's another sample problem, so sometimes you might have to choose, well, where am I going to go and try to get a metal from? Which ore should I choose from? So here we have various iron ores. We have hematite, magnetite, siderite, and we have to figure out where you're going to go and focus your efforts. You have the same quantity of each ore, 400 kilograms, but which one is worth more of your time? You can probably try to figure that out using your mass percent and percentage composition concepts. So I recommend you try this out, compare your answers with peers to make sure that you're on the right path. Show all your work, show all your units. You don't want to just make a guess. You want to justify your answer using the numbers, right? That's what matters in the real world, using numbers to justify your decisions. This problem is a bit more of a challenge. Don't jump to conclusions when doing this problem here. It's very, very similar, but look at the extra information that's given to you. So this is, if you really want to extend that knowledge, try it out. I don't recommend that you jump to the answer right away. The answer is done in this YouTube link here. Try to work it through yourself, see what mistakes you get, and then learn from those mistakes afterwards. But don't let a question like this confuse you. You're not going to see many like this in a test or a quiz. But it is a good thinking one, and something that you should attempt and you should be able to try to solve, because sometimes you will be given problems that you haven't seen directly in your textbook or seen directly in your notes, and you have to think a little bit outside the box, and that's part of learning. A few more practice problems will be included on the following slides along with some solutions, and you can attempt those before looking at the solutions. Don't just look at the solutions and say, yeah, I think I could do that if I had to. Actually try it out to see that you could do it. This here is a really cool video of a demonstration. It's a reaction that happens between sugar and some concentrated sulfuric acid, rather, so H2SO4. What you do is you basically put a bunch of sugar in a beaker, and You add some concentrated sulfuric acid to it, you stir, and then this big mess happens. And so this big mess is a big tower of carbon, which you might have heard of in the incomplete combustion portion of your lessons in the first unit or second unit. Take a look at this video, because after you watch this video, on the next slide you're going to see a thinking style question. This is a lab that could be done to help you figure out the mass percent of carbon in sugar, in sucrose. So this is the thinking question. You can attempt this one over here first, but then read this carefully. Try to design an experiment using that video that we did to figure out the mass percent of carbon inside of sucrose, which is just table sugar, the sugar that you put in your coffee at home, C12H22O11. So design an experiment, try to have some logic behind your design, write out steps, and then explain the logic behind why you're doing those steps and what you're going to weigh, what mass you're going to try to figure out, and then what data are you going to use. Do you need the mass of a compound? Do you need the mass of the carbon? Think about how you're going to work through this in order to figure out the mass percent. You're a scientist. You're not just someone who memorizes and regurgitates information and copies exactly what we do. You need to become better than that. So again, look through it. Try to think about what you're going to do to design this experiment. Think about any errors that you might encounter, difficulties that you might encounter throughout. There are some more practice problems for you to attempt here, along with the practice problems from your book on your outline, and also from the extra sheets given to you in class, and from the problem set that was designed for you.